In the last video, I ended by talking about the internal energy of a substance and how that relates to the temperature that that substance has, and it was written with the letter U. And now we're going to talk about heat, which is the letter Q, or is given the variable Q, and how that relates to temperature. So a lot of times people have the misconception that heat and temperature are the same thing, but the idea of heat is really the transfer of energy from one substance to another that's based on the temperature difference, which we know the temperature difference is based on the amount of energy that the particles that make up whatever that substance have, kinetic energy specifically, and how much those particles are moving. So heat is not a measure of temperature, but rather it's a process in which temperature is regulated. So the faster the moving the molecules we know, the higher the temperature is. And so the whole idea of transfer of heat is really about collisions between the particles. So heat is always going to transfer from higher temperatures to lower temperatures. And the reason is that the movement of heat is results from when two substances come in contact with one another, and if they have a temperature difference, the particles of the higher temperature are going to have a lot more energy, and they're going to collide with the lower energy particles and transfer their energy to it through collisions. So this is really what the movement of heat is the collisions between substances, right? And the idea of this movement or this loss is what thermal energy is. So we've pretty much left it out of our law of conservation of energy so far, but now we're going to start to integrate it. So what is the difference then between the thermal energy and the temperature? Well, the thermal energy is the sum total of all of the energy of the particles that an object has. And the temperature then is the average kinetic energy of the particles. And we'll come back and we'll look at this idea of thermal energy and internal energy and relate it to the law of thermodynamics and how gases can do work in a later video. All right, so heat energy can be included into our law of conservation of energy, and we can calculate it using this equation. So we did use this equation if you've taken chemistry. So Q is heat, or the amount of heat energy, and it's in joules. And M is the mass of a substance. C is the specific heat, and the change in T is the change in temperature. So essentially what this equation means is it quantifies the amount of heat energy that it takes to heat up a certain mass of something. So that makes sense. If you've got a whole lot of it, it's going to take more energy to change its temperature. The amount that you change its temperature is going to be directly proportional to the heat. And then there's this idea here of specific heat. So specific heat is a physical property of matter. It's pretty much how easily something can conduct or take up heat. So metals can change their temperature very easily, whereas other substances like water, it takes a lot of energy to change their temperature. So this is a given based on what the material is. And here you can see that it uses degrees Celsius, but you can also have this in Kelvin. It's just important that you make sure that your specific heat unit is always in the same units as what you're trying to quantify. All right, so the idea of calorimetry is really using the law of conservation of energy in order to talk about the transfer of heat, and it's a process in which we can quantify that. And so essentially, this equation says that heat energy is conserved. So whatever the heat energy lost by one substance must be the heat gained by the other substance. And so quite often what we can do to determine the specific heat of a substance is to place something into water and compare the change in the temperature of the system. And using the idea of Q lost and Q gained, we can figure out what the specific heat of an unknown substance is given the known specific heat of water. And this will actually be a lab that we're going to do, and so you'll be able to see this happening and then quantify it. All right, now there is energy that is required to actually change the state of something or to undergo a phase change. So the Q equals MC change in T, that is to change something's temperature. But in order to melt something or to boil something, or if we think about it in the opposite way, like if we're cooling something down, removing heat to freeze something or to condense something requires an exchange of energy. And so during these processes, the heat energy is not going into changing the temperature of the substance. If you boil water, the water is going to stay at 100 degrees the entire time. So where does that heat energy go? That heat energy goes towards breaking the bonds of in between the water molecules, or the intermolecular bonds. So we need a way in order to quantify this. And so we have this equation, and it looks a little bit different than it did for you in chemistry. So it's M times L, where L is the latent heat of, so it could be a fusion or it could be a vaporization, just depends on whether or not we're boiling or we're freezing. So fusion is the idea of freezing or melting, depending on if we're talking heating or cooling, and vaporization is for boiling or condensing. And it's a constant value. It's a constant, just like specific heat is for a substance. But again, the more mass you have, the more it's going to take to, more energy it's going to take to undergo the phase change. So this right here is an example of a heating or a cooling curve, and it should look familiar to you. So on one axis we have temperature, and on the other axis we have energy supplied. So if we look at the graph like like you traditionally do from left to right, this is a heating curve where we're adding energy over time and the substance is changing between states of matter. So down here, if this is the melting point right here, that means down here it's a solid. So it's taking some energy in order to change the temperature of the solid. And then there is a period of time here where we're adding energy to the system, but we have a flat line, so the temperature is not changing. And that's when we have this idea of latent heat of fusion, or the required energy to change the state. And then as we heat it as it's a liquid, we are increasing the temperature. So that's going to require some amount of energy. We could quantify using Q equals MC change in T if we knew the mass and the substance. And then over here we get to the boiling point. So here you see the latent heat of vaporization, and there's a period of time in which there is no change in temperature, and therefore the energy that is happening here is going to changing the state or breaking those bonds. And then again, here we would be a gas or even hotter, higher energy particles. And we can increase the temperature of the gas, so we would get the Q equals MC change in T here. So it's important to be able to understand all the parts of both a heating and a cooling curve. But again, this should be review from chemistry. All right, so in the next video, we'll start to talk about gas laws, and then we'll get into thermodynamics.